Hello, good evening. Welcome to today's session. Today will be the last session for this problem solving uh, classes by me. So today we'll be dealing with revision questions, randomly chosen, majorly focusing on numerical questions. The last weeks we had discussed, I think, up till uh, week five's numerical problems. So we'll be doing the 6 weeks, I think ninth and 10th weeks numerical problems. In between week six, numerical problems were remaining, so that we will be just going through in today's class. Apart from that, some chosen problems, numericals from all of the lectures. We'll be just doing it for practice, so that that will help you for your when you attend the exams. So yeah, maybe wait for a minute more and then move on to the session. So like I said, I hope I'm audible, right?
Yes, you are audible.
Okay. So last week, I think we finished week five's numerical practice problems. We'll be starting today with week six. Then we'll go to week 12, I think in 10 and 11, there are in the numerical problems. So we'll jump on to week 12's lectures, numericals, and then we'll randomly do some from all the lectures. So let's move to the week six practice problems. So you can take your time and try to do these problems. This is about filtration unit, sorry, aeration, sedimentation, and coagulation. So they have given the design of a rapid mixing unit, the detention time and velocity gradient. With the velocity gradient value, detention time value, dynamic viscosity value. They are asking you to find the power per volume. So it requires the knowledge of just one particular formula. If you know the formula, continue. Otherwise, I'll give you the formula and you can do the problem. So at this point, it would be good for you to recall formulas from every lectures. Because often the numericals are just direct substitutions in the formulas. So you can start doing and then provide me with the answers. Sangamitra, do you know the formula for the finding out the power in the rapid mixing unit?
Is it some one formula was there, rho QH something?
Okay, that formula is a general formula for power. The one with the velocity gradient is mu Vg, the product of the dynamic viscosity, volume, and the velocity gradient, mu Vg square. So if you multiply all the three values, you will get the power watts, power in units of watts. Here they have asked power input per unit volume. In that case, you'll have to just reshuffle the variables in the equation and find the answer. The power equation is P is equal to mu Vg square. Mu is dynamic viscosity, V is the volume, G is the velocity gradient. if you can try the problem, and if you're stuck at some point, just let me know. We'll move on to the solution. Okay.
Is it 72?
Okay, let's move. Check the solution. Right. The answer is 72 watts per meter cube. So, like I said, the dynamic viscosity is given in Newton second per meter square. Velocity gradient is 300 per second. They have asked for the power per unit volume. So, you can actually take the volume term down and just find the product of the dynamic viscosity and G square, which is again 0.8 into 10 to the power minus 3 into 300 square, which will give 72 watts per meter cube. So, that one's answer is right. Let's move to the second problem. So water is flowing into a clarifier with an inlet pipe diameter of 800 mm. A detention time in the flocculator and clarifier is 30 and 120 minutes. The surface overflow rate is given as 36 meter cube per meter square per day. Velocity gradient is given as 40 per second. Consider the flow of 60 million liters per day and the depth of the flocculator basin. The first question is to calculate the flocculator diameter. And the second question is to calculate the diameter of the clarifier. These are the answers. You can do the problem and verify the answers. For those of you who are entering newly, there's a problem given here. You can try the problem, and the answer is also provided. In case you are not able to get the answer, just let me know. We'll discuss the solution. This is basically a practice session.
For question number 2, it is 23.03, so around 23.
Okay. Okay, Sangamitra, shall we move to the solution?
Yes, you can move. I'm doing, but you can proceed.
Yeah, so let's check the solution. So they've given the discharge is equal to 60 million liters per day. Converting it into meter cube per second, we'll get 0.694 meter cube per second. Diameter of the inlet pipe provided is 800 mm. So we can find out the area of the inlet pipe as pi d square by 4. Convert this to meter, and we find pi d square by 4 is equal to 0.502 meter square. For the flocculator, the detention time given is 30 minutes. So the volume of the tank would be the flow into the detention time, which is nothing but 0.694 into 30 minutes. So 30 into 60, 1249.2 meter cube. Now depth is given as 3 meter. So the effective area required, if you divide this volume by the depth, you will get this answer for the surface area. And the effective area will be the total flocculator area minus the pipe inlet area. So when you do that, we'll get this answer. From this, you can find the diameter of the flocculator by using the pi d square by 4 value again. we have the area, you can find the diameter, which is almost equal to 23 meter. The same way you can find it for the clarificator also. Clarificator also, we have the area of the inlet pipe, and detention time is also given. Using the discharge, you can find out the volume of the sorry, here the effective area, the surface overflow rate is given. So when you divide the flow by the surface overflow rate, you will get one area. That area you have to from that area you have to remove the flocculator area. Then you will get the effective area again. You will get the diameter of the clarificator by using pi d square by 4, which is coming around 52 meters. So the glitch here is, or the tricky part here is the diameter of the inlet pipe. Since inlet pipe is actually flowing into the flocculator, from the inlet pipe, water is flowing into the flocculator. So you need to deduct the area of the pipe from the flocculator area and then calculate the diameter of the flocculator. In case of the clarifier, you have to deduct the area of the total flocculator area. The flocculator area from the total flocculator area. The question here asked is not the diameter of the clarifier, I believe. Calculate the diameter of the clarifier is a question asked. What have they found here? So they have found out the area of the diameter of the clarifier. Okay, that is again an issue with the question. Probably, Sangamitra, you might have not been getting the answer due to that fact. Here, if we are finding out the diameter of the clarifier, you will get this effective area value and then directly use pi d square by 4 value for this area. Here, this problem or the solution provided here is for clarificator diameter, not the diameter of the clarifier. Although the question asked is that, so maybe that is why you might not be getting the answer. So that's an error from my part. The question asked is different, but the answer that I provided in the correct answers portion is the diameter of the clarificator. So if you
Actually,
use,
in the
yeah,
material also in similar way
yes,
it was
yes,
solved actually.
I've used the assignment questions from
Yes.
that material only. So that error will be being projected over here. So if they're asking for the clarificator diameter, you will just have to remove the flocculator area from the total clarificator area and then find out the diameter. Else, if they're asking for the clarifier, you can use this solution and find the diameter. Okay. Now next is a question on filtration. They've given a rapid sand filter of dual media, 0.5 meter sand layer and 0.4 meter anthracite layer. They've given the filtration rate of the media as 9 meters per hour and mean size of anthracite and sand as 1.4 and this value. Porosity of anthracite and sand as two values. Grain sphericity as 0.75 and has asked to find the head loss in the filter. Kinematic viscosity value is also given. So in the earlier classes, we learned about Darcy-Weisbach's equation and finding the head loss through that equation. This is another equation that helps to find the head loss in a clean filter. It is Karman-Kozeny equation. In Karman-Kozeny equation, this is the equation. K is a dimensional coefficient that has got values for sand and anthracite. V is the filtration rate that has also been provided in this question. A is the grain surface area, and A can be found out by multiplying the sphericity of that grain by the diameter size of the grain. So here sphericity is given as 0.75 and diameter of the particle is also been given. So if you multiply those two, you will get the area of the grain surface area. Now V is the grain volume. So in order to get the grain volume, you will have to multiply the we don't have to find the volume separately. This part of the equation. Let me go on the laser point. Okay, so this part of the equation can be found out using this formula 6 by phi into d, where phi is the shape factor or the sphericity. In general cases, one is the value for spherical particles and 0.7 is the value for sand. But in this question, they have already given the grain sphericity as 0.75. So in place of this phi, you can use 0.75, and d is the size of the particle. That's the diameter of the particle, which is also been given here for anthracite and sand. So in this question, what you will have to do is you'll have to find the head loss for two materials separately and then add it to get the total head loss, because here they've said 0.5 meter sand layer is placed below 0.4 meter. So anthracite layer will come first, then sand layer will come first. Head loss will be one for anthracite, head loss will be another for sand layer. So all together, we'll have to add both of the head losses to get the total head loss. So again, here they've given the kinematic viscosity value. We know that kinematic viscosity is equal to mu by rho. So directly you can multiply this kinematic viscosity value in here. L is the, here L value is also been given, a 0.5 meter sand layer. That is the depth of the sand layer and is placed above 0.4 meter anthracite layer. So length is also given. L value is also given. So direct substitution, only thing you need to know this formula. This epsilon value is the porosity. That is also given. Here you can see it's a filter porosity. Porosity value is also been given for anthracite and sand. So this is nothing but a direct substitution problem. Possibly there is no change in the units. Let's see. Yeah, you will have to change the units of all these two meters in order to get the values. So just be careful of that. Other than that, it is direct substitution. You can start doing the problem and give me the answer. You're supposed to find H over here. So L, you will have to take it here. Since V is the small v is the filtration rate. In case filtration rate is not given, you can find it out using the surface area. If the surface area of the sand filter is given, you can find it out by dividing the discharge by the surface area. But in this case, since the filtration rate of the media is given as 9 meter per hour, you can directly substitute it in this value over here and do the problem. Again, something to be careful of, this value is given in meter per hour filtration rate. So you standardize the units for all of it and then find the answer. So these will be the answers that you're getting. You can verify the answer after doing. I'll give you some time, then we'll move on to the next. Are you able to get the answers? Either one material. Maybe you might not get the exact answers because in this problem they have taken the K value as 5 standard, even though it's 6 for anthracite. So when you do it for anthracite, so there might be a slight difference in the answer because you might be considered 6 as it is shown over here. But in this problem, they have taken it as 5 only, that they haven't mentioned anywhere, although they have considered 5 only for the K value. So probably whatever your answer, the answer that you're getting might vary slightly because of that change in value. Other than that, everything else is the same. So I'll move to the solution. So this is the simulation, the solution for anthracite layer and sand layer that has been provided. Here they've provided 6 by 5 into D. They have used it in this form, A by V. I don't know why. It's V by A. Okay, irrespective of that, this is the formula 6 by 5 into D. 5 is, or this psi or 5 is the sphericity. So 6 by 0.75 into 1.4 is the diameter of the particle into 10 to the power minus 3 because it has been given in millimeters. Velocity has been given as 9 meter per hour, so they have converted to meter per second. Length for anthracite has been given as 0.4 meter. Kinematic viscosity, direct substitution is equal to mu by rho. In this equation, they have given it as mu by rho. So you can directly substitute, multiply this K value with the kinematic viscosity. E is the porosity, which is given as 0.5 and 0.55 for anthracite and sand layer respectively. You will get the anthracite calculated value is 0.0296 and sand calculated value is 0.545. Probably when you multiply K value as 5. So the total head loss is equal to addition of both of these layers that is going found out separately. This is the Karman-Kozeni equation. If they ask if all these porosity and sphericity and all is given, you know that you need to use that. In case the friction factor is given, you know you need to use the Darcy-Weisbach equation to find out the head loss. So what is the status, Sangamitra? Were you able to do something?
Yes, I did up to anthracite.
Okay, did you get the answer for anthracite?
I have just written. I have not done entire calculation. I'm doing it actually,
Okay,
but
okay,
I could able to means gather all the data and then I'm doing the calculation.
okay, okay. So good. How about we move on to the next question? Hmm, don't look at the answer. I'm sorry that I avoided the answer. So, wait, 1 second. Yeah. So this is the question. These are the options. I'll give you the answer also. Filter is designed at a loading rate. The surface loading rate is 150 for a flow rate of 300 million liters per day. The maximum surface area per filter is limited to 50 meters square. What is the number of filter beds that is required? So we have the discharge which is Q, the surface loading rate which is 150. Find out what is the surface area first. And then using this data, you can find out the number of filter beds. Very simple question. You can try this out. Sangamitra and Lingaraju, you can try this question out. It is a very simple question. Again,
Yes, I am doing.
okay. So let me know. I'll move on to the next question after you get the answer.
Yes, it is done. Actually, area is 2000 meters square. 2000 by 50. It is coming out to be 40.
Okay. So here they given the discharge converted into meter cube per second because and the surface loading rate also into meter cube per second or meter cube per day again is enough. Divide it, you will get the area of the tank as this one, and then number of beds required for number of beds required is we know the area of each bed, so when you divide it by this you will get 40 filter beds. Now let's move on to the week 10. So we covered 2, 3, 4, 5, 6, 7, 8, 9 weeks numerical problems in the previous sections. Now what is remaining is week 10's practice problems. Regarding the pricing and the slab data. So this is one problem which we had discussed in the lecture. But and this one problem is being given in the assignment questions. So maybe you can try this out. City is charging based on a 4 slab increasing block tariff structure. It is rupees 7 for a consumption of 0 to 5 kiloliters per month. Rupees 10 for a consumption of 5 to 10 kiloliters per month. Rupees 15 for a consumption of 10 to 20 kiloliters per month, and rupees 25 for a consumption above 20 kiloliters per month. So this person is using 45 kiloliters per month. So what would be his monthly water bill is the question. So we had discussed this problem, and in that problem we had, a common mistake everyone did was to multiply directly with this 25 value, which was not how this problem was done. You have to segregate the consumption based on the slab and then charge each consumption value corresponding to that the money that is deducted for that much money that is charged for that much amount of consumption, and then find out the answer. I'll give you again 1 to 2 minutes to do the answer. This is just another very simple numerical. If my memory is right, the answer comes to around 860 rupees or something. So you can verify your answer if that's what you're getting.
Yes, it is rupees 860.
Yeah.
5 plus means 45 kiloliter. We can divide 5 plus 5 plus 10 plus 25.
Correct. So the first 5 kiloliters is charged 7 rupees. The next 5 kiloliters, totally if he uses 10 kiloliters per month, the first 5 will be charged according to first slab, and the next 5 kiloliters he's using will be charged according to the second slab. Then again, for an extra amount of 20 kilo, totally if he uses 20 kiloliters, first 10 kiloliters are being charged according to the first two slab. The third 10 kiloliters that he's using will be charged according to the third slab. What is remaining out of 45 is 45 minus 20, which is 25 kiloliters. So 25 kiloliters will be charged according to the fourth slab. So when you totally calculate, the bill he will be getting is 860 rupees. Again, in this, in case of the above mentioned question, that is 45 kiloliters of him using, if he is willing to pay only a maximum of rupees 650 as his monthly water bill, what should be the maximum monthly water consumption for the household in kiloliters per month? So although 860 rupees is coming, he only wants to pay 650 rupees. I mean, he's setting a budget to 650 rupees. So in that case, if he has to pay 650 rupees, how much reduction in water quantity that he's consuming should he do? From 45 kiloliters to how much less water should he consume is what the question is the question being asked here. So again, this is just you can try this question out. I don't think so solution has been provided in the assignment problem, so we can discuss it. Just give it a shot and then we'll move on to the solution. If you're not getting, please let me know. I'll move to the solution directly.
Actually, this question was asked in the assignment. So in previous question, as we did 5 into 7 plus 5 into 10 plus 10 into 15 plus 25 into 25.
Yeah.
So in last part, so I just did x into 25
Correct,
and equate it with 650.
650, correct. You're right. So that's exactly is how this is computed. So the first three slabs is consuming 25 kiloliters. That is accounting to only 235 rupees. So whatever extra amount is coming is what is being charged in the last slab. So the quantity used for 235 rupees is 20 kiloliters. And if he wants to pay only 650, then 650 minus 25, 415 rupees is what he will have to pay extra. So in order to pay, I mean, if he has to pay 415 rupees, he has to use only 16.6 kiloliters instead of 25 kiloliters. So his consumption will be 16.6 plus 5 plus 5 plus 10, which is 36.6 kiloliters. I believe you that will be the answer that you'll be getting, because that's what the range they have given, 30 to 40. So this is how this problem will be done. Now, this is another question, also one which we discussed during the weekly sessions. 0.2 million household is aiming to recover 50 million by implementing the uniform tariff model. If one household is consuming 30 meter cube of water and pays 450 rupees water bill in a month, what would be the tariff under a uniform tariff structure? So these are the formulas for flat rate. Here they have asked uniform rate, although if this question is being asked in the form of a flat rate, this is how they will compute the monthly tariff. That is, what is the amount to be recovered divided by the number of connections. In a flat rate, what is the quantity that is consumed is not taken into consideration. Every household will be charged a monthly bill, and the monthly bill is based on the number of connections, not the volume of the water that is consumed. But in case of a uniform rate, it is based on the volume of the water that is being consumed. So in order to recover in order to calculate the monthly bill, they'll be dividing the amount to be recovered by the consumption volume of the water. So this is the difference between computing monthly tariff through flat rate and uniform rate. Again, here they have asked through uniform tariff structure. So, so in this problem, there was one confusion in the last session where when dividing by multiplying this households with the water consumption and dividing the operational cost, when you divide 50 million divided by this household into 30 meter cube, we are getting a lower value of answer. But instead, when we do 8.33 rupees per meter cube is the monthly tariff per meter cube charged if we have to recover 50 million rupees using the uniform tariff method. But then again, if the person is paying 450 water bill in a month, when we divide 450 by 30, we are getting rupees 15 per meter cube. I believe it is the largest charge that is being considered to recover the amount. So rupees 15 is what is being will be the correct answer. In the earlier question, that is in the previous week's question answer session also, we got a different value of 6 rupees per meter cube and 8 rupees per meter cube. That is probably because when you do it in this way, by dividing the monthly bill by the monthly consumption, whatever amount is being charged will be the amount that is being applied for the tariff amount rather than the wholesome value. So whichever is larger probably will be the answer. So maybe you can take that into consideration.
Okay, that means in this case the answer will be 15.
Yes,
15
right.
per meter cube.
Right.
Okay,
So you can do the computation both
I
ways.
have done actually 8.33. That is why it is showing wrong.
Yeah. So I think that is the possible explanation, I believe, because in both cases they are taking the larger value. So you can do the computation in both ways, and then whichever is the larger value, you can write the answer as well. I believe so. That is why they are choosing this 15 rupees instead of 8.33 rupees. Since both the problems are solved in that way, I'm still not sure if that is why, but then that is, I think so, I believe so. So you can always do it in both ways and then you write in the bigger answer, bigger value. Okay, now regarding the same question, we've been asked to find the average water consumption per household. Were you able to do this problem also, Sangamitra?
No, I have not done this.
Okay, you can try it out now and then we'll move to the solution. So we have the total money, the monthly money, the per household consumption. So you've been asked to find what is the average water consumption per household. So using all the data over in this question, you'll be able to find out. So how about we move on to the solution? So we know that for uniform rate, it is the amount to be recovered by the total consumption. So here, if you want to calculate what is the average amount that is to be charged per household, we'll divide the total amount, which is 50 million, by the number of households, which is 0.2 million, and you will get 250 rupees is what we have to charge per household. But at the moment, 450 rupees is being charged for 30 meter cube of consumption per month. So 450 is being charged per household. So what that is per household is using 30 meter cube. So if 250 is to be charged by unitary method, what you can do is you can multiply 250 by 30 divided by 450. So the average consumption per household will be 16.67 meter cube, and it is I think why this extra amount is coming is because as the slab increases, what happens is the charges will be charged for the services also. So if the average consumption is 16.67, they'll be able to recover the operational maintenance charges. So this is how this question is done. I'll repeat again. First, we'll calculate the tariff based on the uniform rate method by dividing the amount to be recovered by the total consumption. It comes to 250 rupees per household, but presently they're charging 450 per household because the consumption per household is 30 meter cube. So if 450 is being charged for 30 meter cube, for charging 250 rupees, what will be the consumption required? You can multiply 250 by 450 into 30, which will give you 16.67 meter cube. Will be the average consumption per month. Okay, now let's move on to another question using pricing elasticity. Again, this is also a direct formula substitution. Pricing elasticity is nothing but the change in the demand by change in the price, percentage change in demand by percentage change in price. Here they have given what is the change in price and the price elasticity also. You're supposed to find the reduction or the percentage change in demand.
%11.
Yeah, correct. So again, if the percentage reduction, say if you are assigning a minus X value, they have said it is reduction. So we are assigning this minus value over here. We've been given the DP value, which is 18 minus 15, and P value will be the initial price. So percentage change in price is 20%. Directly substituting in this formula, minus X by 20 will give you minus 0.55. So minus X is equal, or X is equal to 0.55 into 20, which will be equal to 11%. So the correct answer is option D. Move on to the next question. Now again, these are some selected out few questions from all the lectures. So this is, I think we have done this problem once, but then you had asked for a flow chart representation of this problem. So I've prepared that. You're supposed to find the weight of the thickened sludge coming out of the gravity thickener. So that first part, I think you can do. And then this for the second part to calculate the percentage solid content TDS in the RO, we'll use the other flowchart diagram. I mean, for the next coming question, we can use that. Here, gravity thickening unit is used to treat 50 meter cube of sludge produced from a water treatment plant. Initially, the solid content is 2.2% and specific gravity is 1.11. Sludge is thickened to 14% solid content by weight. What is the weight of the thickened sludge coming out of the gravity thickener is the question. So in order to get the volume by volume, this percentage value will be volume by volume converted to liters and then apply the initial solid content. You will be doing this problem, right? So this problem is basically nothing but first we need to convert the 50 meter cube to the liter value. That is giving us the volume of the sludge. The 2.2% is giving us the volume of the solids by volume of the sludge percentage. 2.2% is equal to the volume of the sludge, volume of the solid divided by volume of the sludge. So when we multiply 50 into this percentage value, we will get the volume of the solid. Now for the volume of the solid, the specific gravity is given. Using the specific gravity formula, you can find the weight of the solid content. Again, they have said the sludge is thickened to 14% solid content. So in order to make this weight of the solid, using the weight of the solid, dividing it by the percentage weight, you will get the weight of the thickened sludge.
Is it 1221 kg per day?
That is the mass of the solid in the gravity thickening unit. They are asked to find the weight of the thickened sludge coming out of the gravity thickener. 1221 is the weight you are getting in when we use the 2.2%. That is, you're converting this to 50 into liters and you're multiplying it by 0.022.
Yes, it is around, is it 8721 like that? Around?
Yeah, correct,
Yes.
correct. So this, the only thing that you need to know is what is this representation. In that case, by using the representation itself, you can divide or multiply and then find the answer. That was for this question. Now this is the question that I was talking about. So here they have said
one more thing. In previous question, you told that sludge volume is given in meter cube. So initially we should convert it into liter, right?
Right.
Actually, yes, I have means kept it in the form of meter cube, and
then you are getting this answer.
Yes.
Okay. I had actually converted it to liter and also I was getting some of the same answer. I don't think so there'll be a much difference because again it is just adding or multiplying 1000, right?
And one more thing, that specific gravity of solid is given 1.11. So have you used it is equal to density of solid by density of water, that is equal to
No.
1.11.
Weight of the solid by volume, weight by volume is equal to 1.11.
Yes, weight of solid by volume of solid.
Yeah. Okay.
Okay.
Okay. So this problem was a little confusing when I'd explained. So I just prepared a flow chart into how this is done. So here they have, we are supposed to find the TDS level in the RO treated water and TDS level in the RO reject. So the question is, where some amount of water from the filtration unit is sent into an ultrafiltration unit, and then again it is sent to a reverse osmosis unit. So when the water is sent from the filtration unit, 15 million liters per day of water with TDS equal to 850 milligram per liter is treated using a ultrafiltration unit. So firstly, the outflow 15 million liter per day is going into the ultrafiltration unit, and the TDS of 850 milligram is also going into the ultrafiltration unit. Now what happens in the ultrafiltration unit? It is permeating, that is, it is treating 100% of the water. So what happens? All this 15 mld will go into the reverse osmosis unit. Permeated water, like treated water, is what is going into the reverse osmosis. All the 100% of water is going to go into the reverse osmosis unit, but it is removing 25% total dissolved solids from the water and then only sending the water into the reverse osmosis unit. So the treated water will contain 25% less TDS. That is, only 75% of the TDS is going from this ultrafiltration unit is going into the reverse osmosis unit. So here we have calculated what is the amount of TDS that is going into the ultrafiltration unit and what is the amount of TDS that is being rejected from the ultrafiltration unit, which are these values. Now, from 850 milligram per liter, 75% of 850 milligram per liter is only going to the reverse osmosis unit. So the TDS in the reverse osmosis unit is only 637.5 milligram per liter. This value is in milligram per liter. In order to get the value in terms of kilogram, weight of it, what we do is we multiply it with the inflow rate, and you will get that 9562.5 kilograms of total dissolved solid is available in this RO unit. Now the question they have asked here is, what is the TDS level in the RO treated water? Now from RO, they are going to treat some amount of water and they're going to reject some amount of water. In the treated water, what is the TDS level is the question. So they have said here, RO has 96% TDS removal in 77% permeate generated. That is, from this inflow rate, only 77% is being permeated. So it will be 77% of 15 mld, which is going to be 11.55 million liters per day. And they have also said 96% of the TDS is removed when water is being treated in this filtered through this reverse osmosis unit. So how much amount of TDS will be remaining? Only 4% of the TDS will be remaining. So 4% of 637.5 milligram is only remaining in the treated water. So that is amounting to 25.5 milligrams per liter. Now when we want to convert it into the weight, we will multiply again with the discharge rate and with the again inflow rate or outflow rate, and we will get it is 295.525 kilogram. Now, the second question is the problematic part here. We are supposed to find out the TDS level in the RO reject. So, RO reject, if you need to find out the what is the amount of solids in the RO reject, totally there was 9562.5 kilograms of solids in the RO. Out of that, 295.525 is only coming into is available in the treated water. In the rejected water, so definitely it will be 9562.5 minus 294.625 kilograms of solid is available in the RO reject. but we need it in the concentration value, that is milligram per liter. So we will see how much is the outflow rate into the RO reject. RO reject will have 23% of this value that is going into RO reject, because we know that 77% is what is being permeated. So remaining 23% will go into the reject. So 23% into 15 is giving you 3.45. When you divide the kilogram by this liters, you will get the value 2686.4 milligram per liter. So this has been solved in the assignment problems. We have also discussed this. I just wanted to give a figurative representation of what is happening in the processes. So this is about this. You can go through this problem for better understanding of what is happening, what is permeation, what is happening when it is being rejected, how to get basically what is happening is the conservation of mass, that is whatever solid is entering will exit. So here when if 212.5 milligram per liter, again if you convert it into kilogram, you will get one value. So if you find this what is going inside this is actually total value minus this value will give the will give you this value in kilogram. So that is what you have to mainly see when you calculate the TDS. We have to actually conserve the mass. So whatever mass, and that for that you have to calculate it in terms of weight. I mean, not in terms of concentration. You have to calculate the mass of the solid that is present in whatever units, and then do the minusing and addition or percentage removal, and then find out the final answer. Convert it to concentration. So that is about this question. This has been solved in the assignments. You can go through this. I think if you study this one problem itself, it will be good enough for solving a lot of the problems that is similar to this. So let's move on to the next problem. This is regarding concentration of alum. So 1 milliliter of solution containing 10,000 milligram per liters of alum is added in a jar containing 2 liters of distilled water. What will be the concentration of alum in this jar water? The answer is B. You can just do it and see if you're getting the correct answer. Again, like we discussed in the earlier problem, this is getting the weight, the quantity in weight, and then finding out the concentration.
Is it 5 milligram per liter?
Correct. The answer is right. So again, the weight of alum in 1 milliliter solution is 10,000 into 1 into 10 to the power minus 3, 10 milligrams of weight. Concentration of alum when the alum solution is added to distilled water will be total weight of the alum by the total volume or total amount of distilled water. So that will be equal to 10 by 2, which is 5 milligram per liter.
Can you directly do that is the B1H1 equal to B2H2?
Yeah, you can. I just wanted to give an explanation to how it is. Again, this is another question about concentration. A brackish water stream, which means it's saline water or salt mixed water, having this much concentration of salt is meeting a fresh water. with this amount of 200 milligrams per liter of salt concentration. Discharge rates are given, complete mixing, and there's no salt going anywhere out. What will be the salt concentration at the meeting point, downstream of the meeting point? What will be the salt concentration at the downstream of this meeting point of the two types of water? Again, similar one. Total weight by total volume.
Is it 600 milligram per liter?
Right. So again, the mass of the salt in brackish water, you'll find it as 10 into 10 to the power 6 milligram per second. Mass of the salt in fresh water as this one. The total mass will be, when you add these two values, total volume will be the these two values added together. Salt concentration will be total mass by total volume, which will give 600 milligram per liter. So again, very similar to the earlier problem. Now let's move on to the water loss, real losses, apparent losses, unaccounted for water, non-revenue water. So here they have given a total consumption of 50 milliliters per day for domestic uses. Meter is wrong. It reads 0.8 kiloliters for every kiloliter. So for 1 kiloliter, the wrong reading is 0.8 kiloliters. Pipeline is also having a leakage. If the rate of the water supply is 2.5 rupees per kiloliter, these are the following things that you need to compute: total water loss, non-revenue water, total water losses, what is the percentage of losses, what is the monetary value of the apparent losses, monetary value of the real losses. So I'll show the questions. Before that, maybe we just refresh the mathematical relations. Unaccounted for water. So unaccounted for water can be found out by either finding the difference of the system input volume and the billed authorized consumption and the unbilled authorized consumption. So we have two types of separation from the system input volume. One is the authorized consumption and one is the losses. In authorized consumption, there is billed authorized consumption also, unbilled authorized consumption also. In losses, there is real losses and apparent losses. Real losses are the losses that is occurring due to leakage. Apparent losses are the losses that is occurring as a result of meter default. So unaccounted for water is nothing but the sum of two losses, which is also the total system input value minus the authorized consumption, which is billed authorized plus unbilled authorized consumption. When you find subtracted from the system input volume, you will get the unaccounted for water, and percentages dividing it by the system input volume into 100. Now, non-revenue water is nothing but the sum of the real losses, apparent losses, and the unaccounted, unbilled authorized consumption. So, if you know the billed authorized consumption, minusing it from the system input value will give the non-revenue water. Otherwise, if we have the real losses and apparent losses values and the unbilled authorized consumption values, we can find out the non-revenue water directly. So here they have asked for the total water loss, which will be the sum of the real losses and apparent losses. So first maybe you can find that out. Total consumption of 50 million liters per day for domestic. So that is the system input volume. Meter is wrongly calibrated. So meter losses is the apparent losses. For that, you can use this meter value computation. And for finding the real losses, you can find out the leakage. Find it out using the leakage rate. So the meter reading is wrongly calibrated means for 1 kiloliter, the wrong reading is 0.8 kiloliters. Then for actual 1 kiloliter, it will be 1 by 0.8 kiloliters will be the correct meter reading. Now we have the meter reading in kiloliters. That if you multiply by the
apparent loss is 12.5.
62 point, okay, yes, apparent loss is 12.5. You can find the real losses. Do you get the real losses, the total losses, Sagnamitra?
Yes, real loss 43200 meter cube per day, and if we convert it $43.2
Correct.
million liters
Per day.
per day.
So we have the real losses and the apparent losses. Total water losses will be the sum of those two, which is 55.7 million liters per day. Now you're supposed to find the total non-revenue water. Since again here there's no total non-revenue water is the sum of the losses plus the unbilled authorized consumption. But there is no value of unbilled authorized consumption provided over here. So what you'll do is total non-revenue water will be equal to again the sum of the real losses and the apparent losses. So that doesn't need any extra computation. Whatever total water loss you're getting will be the answer for the B part of the question also. Now moving on to the percentage of water losses. Percentage of water losses will be the total water losses divided by the system input volume into 100. So again over here, the C part they're asking you to find the percentage losses. Percentage losses is the total water loss by the system input volume. System input volume will be whatever is being consumed plus whatever water is being leaked. So consumption is 50. The water loss is computed is 55.7. Total volume of water that is entering is 105.7. So you need to divide it by that value to obtain the water losses percentage. The fourth part of the question is what is the monetary value of the apparent loss? They have given 2.5 rupees is what is being charged per kiloliter. So apparent loss here is 12.5 million liters per day. So converted into kiloliters per day and multiply the charge of that into this value, you will get what is the amount that is being lost because of apparent loss. Again, the fifth part of the question is amount that is being lost as a result of real losses. Again, multiply 2.5 by 43.2 million liters per day and you will get the amount that is were you on track, Sangamitra?
Yes, I have done.
Oh. So this is how this problem is, again, this problem covers almost computation of real loss, apparent loss, total revenue, water. What is the total supply in the system? The only glitch that I see here is the probability of taking this 50 million liters as a system input volume. But you have to add the leakage or amount of water that is being leaked also along with this 50 million liters per day in order to get the total water that is entering the system. It's not total water that we are consuming that is used as the system input volume. It's the total water entering the system, which also includes the water that is leaked off. So that value also should be added to the consumption water to get the total system input volume, and that is what you have to use as SIV value. Now, another part in this is the minimum night flow analysis. Minimum night flow analysis is the kind of analysis where in a particular period of the night, if there's excess use of water, then you understand that it is some kind of leakage that is happening, and it is computed by minusing the minimum night flow by the legitimate night flow. And from that, you can find, using the pressure leak relationship of Lambert, you can find out what the pressures will be given, and the leakages, the leakage discharge rate of leakage also will be given. You can find out the what is the leakage at a point, by measuring the pressure value. So the next problem is based on that. So utility is carrying a minimum night flow analysis to quantify the leak volume, and the minimum night flow MNF value is 60 liters per second, and the legitimate night flow is 80 liters per second. You've been asked to find out the real loss. So real losses, you can, I just explained this one, maybe Sangamitra, you can try it. You can apply it in that Lambert formula and find out the pressure leakage. You can find out the average pressure, average leakage for the pressure value that is given. Also the real losses using the formulas that I just explained, and just let me know the answer.
Is it 388.97?
Yeah, correct. So the you can find the real losses, estimate the average daily real loss for the DMA if the 24-hour average pressure is 16 meters. So initial pressure is 23 meters, which is equal to P naught. P1 is equal to 16 meters. Then L naught is equal to 520. You're supposed to find L1. Direct substitution in the formula. N value is equal to 0.8. You'll get the answer 389 liters per second. Correct answer. Okay, so let's move on to some random questions. You can tell the answer, and you're supposed to match the following. If you don't know the answer, we can just revise it and go on forward. Here, three types of reservoirs are given: clear water reservoir, service reservoir, balance reservoir. They are located at three different parts of the water distribution network. So where all are these reservoirs located? Okay, so this is schematic of the um, three types of reservoir. Clear water reservoirs are located between the source of the water and the pumping station. Service reservoirs are where water is stored for distribution. So it is located between the pumping station and the user's point. Then the clear water reservoir, clear water reservoir is located between the pumping station and the source of the water. Distribution of service reservoir is provided at the center point of the source and the distribution network, and the service reservoir is provided below this. The balancing reservoir is provided after the service reservoirs in case there's some uh, network issue, the electricity issue to supply water during low water demand. So the answer is B, correct, Sangamitra. Clear water reservoirs is before the distribution network to store the treated water before pumping. Service reservoir is within the distribution, located at the center of the demand, that is between the source and the consumer end. Balancing reservoir is within the distribution network for storing at low demands and supplying during peak. So first it will be clear water, then it will be service reservoir, then it will be the balancing reservoir. Now, what is the effective volume in a service reservoir denoted by? Is it there are four types of classifications for a service reservoir: operational storage, uh, equalizing storage, emergency storage, and dead storage. What is the effective volume in a service reservoir? Is it equalizing storage plus emergency storage, operational plus equalizing, emergency plus operational, or none of the above?
Is it A?
Correct answer. So, like I said, operational storage is there, equalizing storage is there. Operational storage, equalizing storage, says emergency or fire storage, and dead storage. Effective volume is equalizing storage plus emergency storage. Total volume is equal to, will include all of this one. Effective volume is the center portion only. Let's move on to the next question. This is regarding the quality of water. What is the correct pair of water quality methods and their method of estimation?
Is it C?
Correct. So here, microbial water quality is done using E. coli test. Total solids is done using gravimetric method. Suspended solids to Wattman filter paper. Total dissolved solids to electrical conductivity, and turbidity is being used uh, by scattering and absorption of light. So the answer is C, total solids gravimetric analysis. Hardness is done using titration with EDTA, using the indicator Aerochrome black tea. What is the reason for temporary hardness in water? Is it caused by bicarbonates of carbon and magnesium, sulfates of carbon and magnesium, chlorides of carbon and magnesium, nitrates of carbon and magnesium?
Bicarbonates. Yeah.
Correct. So temporary hardness is caused by bicarbonates of carbon and magnesium. Permanent hardness is caused by the sulfates and chlorides of carbon and magnesium. So aeration of water is done to remove the suspended impurities, colored, dissolved solids or dissolved gases.
Dissolved gas.
Correct. So for these are the methods of removal for the different types of impurities. For suspended impurities, we use sedimentation. For color, it is using oxidizing agents. Dissolved salts also, methods like reverse osmosis. When it involves gases, it is to use methods like aeration. Now, water distribution systems are sized to meet the maximum hourly demand, average hourly demand, maximum daily demand and fire demand, or average daily demand and fire demand. What is the demand estimate used for designing a water distribution system?
Is it C?
Correct. It's a maximum daily demand and the fire demand. So these are the design rates for different types of water supply systems. Maximum hourly demand is used when we are designing pumps and service reservoirs. Average hourly demand is used for distribution systems, components of the distribution systems like valves and all. Maximum daily demand and fire demand is for the water distribution system, that is consisting of all of the pipelines, the valves, everything. Average daily demand and fire demand is for water treatment equipments, and monthly variation is used for design of storage reservoirs. So having an idea about this also would be good. So that will be today's weekly session. Sangamitra, thank you for attending the session, and it was a pleasure working with you. You've been consistent in all of the classes, and all of those who have joined the sessions, all the best for the exams that is coming up. Do well. So this will be my last weekly session. Thank you for attending the session.
Thank you very much also. It was very good to interact with you.
Thank you so much.
Nice meeting you.
Okay, I hope the sessions were useful to you and everyone who attended.
Yes,
so,
yes, it's very useful. Very useful.
Thank you so much. So all the best for the exam, Sangamitra. I'm sure you'll do pretty well because you've been really good in answering all the questions. So all the best.
Thank you very much.
Okay, then. Bye-bye. Good night.
Bye. Bye.